Hello students, today in this video we are going to start with chemistry. So let's see which topic we are going to take in this video. The topic is part 2 of rate of reaction and chemical equilibrium. As we have already done the rate of reaction part, so now we'll be doing the chemical equilibrium. So we'll start with the basic thing that where this equilibrium is achieved and how it is achieved and what are its type and what are the characteristics of this chemical equilibrium. So are you ready to start? So let's start with this interesting topic. Topics to be covered in this video are types of equilibrium, equilibrium involving dissolution of solids, general characteristics of physical equilibrium, equilibrium involving in the chemical process, and the factors affecting the state of equilibrium, that is Le-Chatelier's principle. So these all topics we'll be taking up. So let's start with the introduction first. So in order to understand about the equilibrium, we should have knowledge about the reversible and irreversible reactions. We know that chemical reaction is that in which reactants combine to form products. So generally how we represent a reaction, we represent that these are reactants and this arrow represents that they give rise to, or you can say they form, this arrow represents this, they form or they give rise to products. This is what is a chemical reaction. So like reactants are forming the products, right, in this case. Now what happens, we have two types of reactions. What is reversible and the other is irreversible reaction. See, reversible reaction is that in which, like I think before starting with reversible, we should do irreversible first. So generally, till now what we have studied about the irreversible reaction. That is a reaction in which the reactants are combining and they are forming the products. Like if I take an example of burning of paper, I'm taking a very, you can say a simple example, burning of paper. Like you have a paper, right? What do? You burn it. That means it combines with oxygen because supporter of combustion is oxygen. So what happens when it burns? It forms the ash. It forms the ash. So generally these are the reactants and this is a product. So in this case the reactant forms the product. But there is no such facility that the product, that is the ash in this case, give rise to paper. We don't have a process like this that in which we can convert ash back into paper. So that means this reaction will occur only in one direction. That is the paper will burn and form ash and that's it. We cannot convert ash back into the paper. Likewise, if we suppose if we want to convert milk into cheese. If we want to convert milk into cheese. How we do that? We take milk, we just heat it and to it we add vinegar or we add a few drops of lemon juice. What happens? This milk gets converted into cheese. This milk gets converted into cheese. But there is no such process that we could apply and convert this cheese back into milk. So we cannot do that, right? So that means this reaction occurs only in one direction. That is the milk on adding the vinegar get converted into cheese. But we cannot convert cheese back into milk. So these reactions are called as irreversible. That is, these reactions occur only in one direction. They cannot be reversed. But we come across few reactions that are reversible. Reversible means we can convert, like if I say I have reactants, I can convert the reactants into product and I also have a phenomena, I also have a process due to which I also have a process by which I can convert this AB back into reactant. Right. So that means in this case the reactants are AB when we are considering the forward reaction and AB is the product. But if the reaction happened to be in the opposite direction, so this is going to be a reactant and this is going to be product and it will occur in a backward direction. So that means there exist few reactions like this that can be reversed. And for carrying out the reverse direction, we have to apply, or you can say we have to provide with suitable conditions. we have to provide with suitable conditions. That is the specific condition of temperature, pressure, catalyst. It can be anything. So I think you got it. That reversible reactions are those in which the products can combine back to form reactants under given set of conditions. An irreversible reaction is that the reaction in which products can't combine to form reactants back under given set of conditions. So how we are going to define irreversible? That is irreversible, the reaction in which products can't combine to form reactants back, like as we discussed about burning of paper. We cannot convert ash back into paper. Now, where we get to see this phenomena, that is equilibrium. Equilibrium is established, or you can say equilibrium is applicable only in the reversible reactions. Equilibrium is seen only in case of reversible reaction. Reversible reaction, we know that is a reaction in which the reactants can form the product and product can also form the reactant back under given set of conditions. So these kind of reactions are represented by double arrows. So these half arrows represent like this, that A and B is reactant in this case, and it is going forward and it is going to be product. And likewise, it can happen in another manner also, where this is going to be reactant and this indicates that AB is going to form product AB, A and B now. So equilibrium is seen in case of reversible reaction. Now I think you got it, that what do we mean by reversible and irreversible, and it is clear also that equilibrium is a certain process that is used or studied in case only of the reversible reaction. It is not seen in case of irreversible. Now what do we mean by equilibrium? What do we mean by equilibrium? Like in this reaction, A and B combines to form AB, and AB also has a tendency to decompose back into A and B. So the reaction is occurring in a forward direction also, and at the same time reaction is occurring at the reverse direction also. So what happens? A point is achieved after some time when rate of forward reaction means the speed with which the A and B is getting converted into AB. It becomes equal to rate of reverse reaction. Rate of reverse reaction, that is the speed with which AB is dissociating back into A and B, and that point is called as equilibrium. That point is called as equilibrium. So at equilibrium, rate of forward reaction becomes equal to rate of reaction, but it is not like that the reaction stops. Only the rate becomes equal, that is the speed with which the AB is getting converted into AB, it becomes equal to the speed at which AB is getting dissociated into A and B. So I think you got it, that equilibrium is a point when rate of forward reaction becomes equal to rate of reverse reaction. Or in other words, we can say that at equilibrium, concentration of reactant become equals to concentration of product. So this is how you can actually denote that this is a graph which is showing the forward rate, and this is the graph which is showing the reverse rate. So this is a point of equilibrium when the rate of forward and reverse becomes equal. So according to chemistry, we can define it in a way that it is a point in a chemical reaction when rate of forward reaction becomes equal to rate of backward reaction. Or we can say it is a state when concentration of reactants become equal to concentration of product. Let's take an example now. We have an equation where nitrogen combines with hydrogen, and it is an irreversible reaction, and they combine to form ammonia. So this is the balanced reaction for it. So this is balanced. So N2 plus 3H2 reversible sign 2NH3. So as we know that this reaction is reversible, so there will be a certain point that is called as equilibrium when rate of forward reaction becomes equal to rate of reverse. That is, the rate at which N2 and H2 combines to form ammonia becomes equal to the rate at which ammonia is dissociating back into nitrogen and hydrogen. And that point is called as equilibrium. And at this point, the concentration of nitrogen and hydrogen will be equal to the concentration of ammonia formed. Right? So concentration of reactant become equal to concentration of product. And you know that how to write this rate expression in terms of the concentration. And if you forget that, how to write that, or if you have any confusion, you can refer to part 1 where we have learned about the writing of the rate expressions. So now let's study about the types of equilibrium. So we come across 2 types of equilibrium. That is the equilibrium which is achieved in case of chemical processes, that is the chemical equilibrium, and the equilibrium that is achieved in the physical processes, that is called as physical equilibrium. So under physical equilibrium, we'll consider all physical processes like the conversion of states and all, and in the chemical equilibrium, we'll consider all reversible reactions. So let's study. So first we are going to do about the physical equilibrium. So let's study about it. So as I told you that physical equilibrium is achieved in all physical processes. And you know that what are physical processes? Physical processes are those in which no new substances form, there is no net energy change, and you also know that the physical processes are reversible and they are temporary. They are temporary. So this equilibrium is achieved in almost all the physical processes. And at this point, or you can say the equilibrium point in physical processes is achieved when the state variables like pressure, temperature, or some other physical quantity becomes constant. That can be pressure, that can be temperature, that can be volume, that can be concentration. So in equilibrium achieved in the physical processes, either of this quantity becomes constant. So let's study more. So let's take an example of physical equilibrium. Let's say we are converting solid into liquid. We are converting solid into liquid. Let's take a proper example. Let's say melting of ice. So when ice melts, it gets converted into water. When ice melts, it gets converted into water. And this forward reaction, that is the converting ice into water, is referred to as melting. And the reverse, that is the conversion of water into ice, is considered to be the freezing. This process is called as freezing. So we can say that in forward reaction, the process is melting. In the forward reaction, we have melting, and in the reverse direction, we have freezing. So these are the 2 processes which you can see in this. So what happened at equilibrium? What happens? The rate of forward reaction, that is the rate of melting, becomes equal to the rate of freezing. The rate of melting becomes equal to rate of freezing, and this occurs at the equilibrium point. And under this physical process, the state variable that becomes constant, that is pressure. That is pressure. So I think you got it. So let's take another example now. Let's say we have an example of sublimation. Let's take an example of sublimation. We know that sublimation is a process in which the solid directly changes into gaseous state on heating, and gas on cooling gets converted back into the solid state. Let's take an example of iodine. We know that iodine show this property that iodine can sublime. When it is heated, it gets converted into gaseous state, and on cooling it again solidifies. So the forward process is evaporation and the backward process is solidification. Let's write. So that means in this case, in the forward direction we have evaporation, and in the backward we have solidification. So what we'll get to see at equilibrium point? We'll see that the rate of evaporation becomes equal to rate of solidification. So these kind of, you can say that equality in the rates of forward and reverse direction is C. And in this, the quantity, that is the state variable that becomes constant, is temperature. So likewise, we can explain different examples. We can also explain the example of conversion of state of liquid to gas in a similar manner. So at equilibrium, in that case, the rate of evaporation will become equal to rate of condensation at the equilibrium point. And the state variable in that case also is going to be temperature, that becomes constant. So I think now we can study about the characteristics of physical equilibrium. So we have seen that in case of physical equilibrium, the measurable properties become constant, like temperature, pressure, volume, or the concentration. They become constant at equilibrium point in case of physical processes. Second thing is seen that physical equilibrium can be established only in a closed vessel. This is very important. Whenever we have to establish equilibrium, it cannot be established in an open medium. We need a closed system for that, right? So it can be established only in case of closed system, or you can say closed vessel. And what happens at equilibrium? At equilibrium, the opposing forces becomes equal. That is, the force which is pushing the reactant in order to convert into product becomes equal to the force which is pushing the conversion of product back into the reactant. So both the forces becomes equal. That makes the rate becomes equal. And the equilibrium is dynamic in nature. This is, you can say, an important characteristic of equilibrium. Like the closed vessel is an important point, even this dynamic nature is an important point of the equilibrium. Dynamic nature means at equilibrium, only the rates become equal, but the reaction keeps on going on. So it doesn't mean that equilibrium the reaction stops. I'm repeating it again and again. At equilibrium, the reaction keeps on going. Only the rate and the concentration becomes constant. At equilibrium, the concentration of reactant becomes equal to concentration of products. That means concentration becomes constant. And the magnitude of the equilibrium value, let's say that equilibrium has a certain value, and let's say it is 6, 5, 7 or 10 raised to the power 2, 3, that indicates that you can say what is the extent of reaction. So magnitude of the equilibrium value gives about the indication to what extent the reaction has taken place. Like equilibrium value is represented by K, that is an equilibrium constant. So if the K value is high, that indicates that the forward reaction predominates. That is, the forward reaction predominates. But if the K value is low, that means the extent of reaction in a forward direction is less. So it indicates that the reverse reaction is much favored. So I think you got it. These are the characteristics of the physical equilibrium. Now let's study about the chemical equilibrium. So chemical equilibrium is that which is achieved in case of chemical reaction, and particularly which kind of chemical reaction? That is reversible reaction. It is achieved in case of reversible reaction. And we know that reversible reaction is that in which reactant can convert into product, and even the product under given set can convert back into reactants. So both the reactions, that is the forward and the backward, keeps on going on, and at equilibrium point, the rate of forward reaction becomes equal to rate of reverse reaction. Let's take an example. Suppose we have a reversible reaction in which H2 combines with iodine, reversible reaction, to form 2HI. This indicates the reversibility, right? So the rate at which H2 and I2 is forming HI is equal to the rate at which HI dissociates back into H2 and I2. Right, and this can be represented by this graph. So this represents the forward rate, this represents the reverse rate, and this is the point where equilibrium is achieved. That is when the rate of forward reaction becomes equal to rate of reverse reaction. So let's do the characteristics of chemical reaction now. So we have seen that the rate of forward reaction becomes equal to rate of reverse reaction. In case of chemical equilibrium, the rate of forward and reverse becomes equal. Catalyst doesn't affect the equilibrium. That is, the catalyst has nil effect on the equilibrium. But it just can help in achieving the equilibrium faster, because we know that catalyst is a substance which increases the rate of reaction without getting consumed or without getting changed. So it can make the equilibrium point achieved faster, but it has nil effect on the equilibrium. It will neither favor the forward reaction, it will neither favor the reverse. It is just going to make that equilibrium point achieved faster. Equilibrium is attained only in the closed vessel. This point is same for both the physical and the chemical, that equilibrium can be achieved only if there is closed system. Because if there won't be a closed system, then what would happen? Obviously, the mass will change, and we know that the equilibrium has a specific quantity, that is, the concentration should not increase or decrease itself. Then only at the equilibrium point the concentration will remain same. So equilibrium is achieved only in a closed vessel, and it can be achieved from either direction, whether you start from A and B and then from AB, or you see it from AB side. So equilibrium can be achieved from either direction. So it's not specifically that we have to start from this side only or we have to start from this side. It can be achieved from either direction. At equilibrium, the concentration of reactants becomes equal to concentration of products, and equilibrium is dynamic in nature. That is, the reaction doesn't stop, only the rate and the concentration become. Now let's learn to derive the expression for equilibrium constant, that is K. Right, it is not included in your syllabus, but in order to understand the equilibrium effectively or efficiently, we should know about its expression also. So let's consider a reaction in which A moles of A react with B moles of B in order to give C moles of C and D moles of D. And this reaction is reversible, so we can see that C and D can give back reactants also. So that means it is a reversible reaction. And though it is a reversible, obviously we'll get to see equilibrium also. Let's write the rate. So we know that, let us consider the forward reaction first. Let us consider the forward reaction first. So in the forward reaction, what do we have? We have AA and BB are reacting to form CC and DD. So let's write the rate for the forward reaction. We know rate of any reaction is directly proportional to the concentration of its reactants raised to their respective moles. So this is how we write. We have already learned in the part 1. So let us write this expression for the reverse reaction also. And we know that the reverse reaction is in which the CC and DD combines to form AA and BB. So rate for reverse reaction will be equal to K, concentration of C raised to power C, concentration of D raised to power D. And we know that if we look at equilibrium point, we have already learned that rate of forward reaction becomes equal to rate of reverse reaction. So this is an expression for forward and this is an expression for reverse. So let us put this values here, and let's put this K as Kf for forward and Kr for reverse. So that means at equilibrium, Kf and the concentration of this at the B is equal to the Kr, concentration of C raised to power C, concentration of D raised to power D. So it's like that. We know that we can equate this value like this. So we'll get the concentration of C into concentration of D divided by concentration of A into concentration of B raised to their respective moles. So let's proceed further. So let's write that expression again. So we had Kf upon Kr, right, is equal to concentration of C raised to power C, concentration of D raised to power D, concentration of A raised to power A, and concentration of B raised to power B. Now Kf upon Kr, that is the rate constant for forward divided by rate constant for reverse direction. This is equal to the equilibrium constant for the overall reaction. So we write it as Kc. So Kc is equal to concentration of Cc, D raised to power D, A raised to power A, and B raised to power B. Right. So that means the equilibrium constant is equal to the concentration of products, because C and D were products, raised to their respective moles, divided by concentration of reactants raised to their respective moles. So this is the expression that actually explains the equilibrium constant. So this is how you can derive it for the complete reaction. But if we want to derive this expression in between the reaction, then Kc is replaced by Qc. That is reaction quotient. That is reaction quotient. So it is similar to Kc. The difference is only that Qc is the point when the equilibrium is not achieved. At equilibrium we have Kc, and if we are looking at the reaction before or after the equilibrium, then it is called as Qc. That is reaction quotient. And at equilibrium, what happens? Kc is always equal to Qc. That is, the equilibrium constant value is always equal to the reaction quotient. So if there is a chance when the both values are equal, that means that specifies the equilibrium point. But if Kc is more than Qc, if Kc value is more than Qc, that means the products predominate. And if Qc is more than Kc, that means the reactants are much, you can say, formed. The reactant concentration is more in this case. So I think you got it, that how we need to write the equilibrium constant expression. Now let's study about the effect of temperature on the equilibrium constant. We know that Kc is equal to equilibrium constant for forward divided by equilibrium constant, or you can say the rate constant for backward reaction. Now, if temperature is increased, we know that rate is directly proportional to temperature, because when temperature increases, the molecule possess more kinetic energy, they undergo more effective collision, and the rate automatically increases. And we also know that rate depends upon K, because the expression is that, like reactants or products, we make use of K, which indicates that they are directly proportional. So if temperature is increased, then the rate is increased, and though the rate is increased, therefore the K is also increased. So that means the extent of reaction, that is up to what extent that reaction will go, whether in forward or backward reaction, backward side, it depends upon the activation energy of the reactants. And due to the reason Rf and Rb, that is the rate of forward and the backward reaction, will be different, and therefore the value of Kf and Kb will be different. So with change in temperature, the rates of forward and the backward reaction will change, and due to which the value of K also change, because the value of K depends upon the R, that is the rate, and rate further depends upon the temperature. Now let's study about the factors that affect the equilibrium. Let's study that what are the factors that affect equilibrium. So the factors that affect equilibrium can be explained on the basis of Le-Chatelier's principle. So this principle states that we know that when equilibrium is achieved, the state variables, that is temperature, pressure, volume, concentration, they become constant. And if we disturb any state variable, like if we are increasing the temperature or decreasing, or increasing, decreasing the pressure, volume, or any state variable, the reaction will get disturbed, and it will divert the reaction itself in a direction where the stress can be reduced, so that the reaction can proceed smoothly. So let's see what is the statement according to Le-Chatelier's principle. It states that if any kind of reaction is subjected to any kind of stress, let's say we have a reaction like this, and let's say in a forward direction, what we are doing, we are supplying it with energy. We are supplying it with energy. So what happened? This energy will make this reaction stressful. That is the conversion of AB to A and B to AB. So if the energy is more at this side, that is left hand side, so it will make the reaction move in that direction where the stress can be reduced. So in this case, A and B will favor the formation of AB. Likewise, if you increase the pressure, then the reaction will shift into that direction where the pressure gets reduced. Or if the pressure is reduced on one side, then the reaction will shift to that side, or you can say equilibrium will be favored, or the reaction will be favored towards that side where the stress due to pressure can be reduced. So let's study all the factors that affect the equilibrium, and let us explain on the basis of Le-Chatelier's principle. So first is the effect of change in concentration. Let's say if we have a reaction, right, like this, And what I'm doing is, let's say I'm increasing the concentration of one of the reactants. Let us increase the concentration of A. So if the concentration of A is increased, what happens? It will start getting consumed more, and due to which the forward reaction will be favored, because the reaction will be stressful on left hand side because the concentration of A molecules is increasing. So it will shift the direction in that side in which the A molecules get consumed. So it will favor the forward reaction. Similarly, if I increase the concentration of AB, then the reaction will be disturbed on this side. So that means under this condition, the breakdown of AB into A and B, that is the reverse reaction, will be favored. So we can write in this way that if concentration of reactants are increased, then the reaction favors products. The concentration of reactant can be for one reactant, or the concentration can be of both the reactants. So any chance, like by any chance, if you are increasing the concentration either of one reactant or all the reactants, the reaction will favor the products. And if the concentration of products is increased, then the backward reaction is favored. Second is effect of change in temperature. So let's take an example again. If I say that A and B combines to form AB, let's say we are providing heat to the reactant side. So this heat will increase the energy on left hand side. So energy will increase, that means the reaction will get disturbed. So it will, you can say, move in that direction in which the heat can be released, because it is absorbed in this direction. So it will favor the direction in which the heat can be lowered. So obviously the products will be favored. Likewise, if I say that heat is released in this case, so in that way, wherever you can say that at any side, if the temperature is being increased, then the reaction will favor to that side in which the temperature can be reduced. So if we increase the temperature, the reaction proceeds in such a direction that heat is absorbed. That is, endothermic side is favored. But if we decrease the temperature, then the reaction proceeds in a direction in which the heat is released. That is, at that time, exothermic side is much favored. So that is the reason we have done that for endothermic reactions, they are favored at low temperature, and exothermic reactions are favored at high temperature. Now let's do it for the effect in change in pressure. So what we have seen that, like if you are increasing the pressure on the left hand side, that is on the reactant side, so it will move to a side where the pressure can be reduced. So how do we come to know that which side is favored, or what quantity other than pressure is favored or neglected in this case? So what happens if we increase the pressure on one side? Let's say we have the reaction like this. Let's say this is ammonia. So let us balance it. Now it becomes balanced. So if we increase the pressure on left hand side, increasing the pressure means, like if we are increasing the pressure, that means moles per liter on the left hand side will increase. So it will make the reaction move in that direction in which the moles per liter you can say present in a given volume decreases. So as you can see that on left hand side we have 4 moles and on the right we have 2 moles. So which will be favored? Obviously if the pressure is increased, so moles per liter gets increased, it will be favored, like that side will be favored which has lesser number of moles. So that means the forward reaction is favored. Likewise, if you are reducing the pressure means moles per liter are decreasing. So what side will be favored? That side will be favored where moles per liter are increasing. So we can write in this way: if we increase the pressure, it will take the reaction towards lesser number of moles, that is towards the products or reactants depending upon where the moles are lesser. And if we decrease the pressure, it will make the reaction proceed towards more number of moles. That can be reactant, that can be product, that depends on the reaction to reaction because moles are different for different reactions. Let's do the another factor, that is the effect of change in volume. So what we know about Boyle's law? Boyle's law is a law which states the relation between pressure and volume. and according to it, pressure is inversely proportional to volume. That is, more is the pressure, less is the volume, less is the volume, more is the pressure. So now, if you say that if we increase the volume, if we are increasing the volume, obviously the moles per liter decreases. The moles per liter decreases. So if moles per liter decreases, that means the reaction is subjected to stress. So according to Lee-Chatelier principle, it will shift in a direction where moles per liter increases, in which on the side in which the moles per liter are increasing. That means it will shift where the volume gets decreased. So it is actually the vice versa of the effect of the change in pressure, because pressure and volume are inversely proportional. So we can write that the reaction moves in that direction which the moles per liter is increased if in case we are increasing the volume. So let's say if we are decreasing the volume, then what happens? If we are decreasing the volume, then moles per liter are increasing. So it will shift the direction into a direction in which the moles per liter are increasing. That is to a side where volume is increasing. Where volume is increasing. Right. So because here what do we have? We have moles per liter more here. So we will shift to a direction where moles per liter decrease, and it will decrease only if the volume will increase. Now let's do the effect of the introduction of inert gas. What is inert gas? Inert gas is a gas that do not react with any other substance, but because it possesses the moles in it, so when we you can say add it to some container or something, so obviously it will affect the moles. Obviously it is going to affect the moles. So whenever we introduce inert gas to any reaction, then what happens? That it doesn't affect the equilibrium. It doesn't affect the equilibrium. But if we introduce an inert gas at constant volume, so the volume is not going to change. That means moles per liter in that given reaction is going to remain same. But if we introduce it at constant pressure, so if we are introducing at constant pressure, so the volume will increase in that case. Increase means moles per liter will decrease, and it will make the reaction subjected to a kind of stress, and it will shift the direction to the side where moles per liter are increasing. Right. So this is what is the effect of introduction of inert gas. So when it is introduced at constant volume, it has no you can say effect on the equilibrium, but if it is introduced at constant pressure, it affects the volume, and due to which you can say that the reaction is subjected to a stress, and it shifts in a particular side, like whether it be a reactant side or a product side. So this is how you're going to write that inert gas introduced at constant volume does not affect the equilibrium. But if it is introduced at constant pressure, it leads to increase in volume, due to which moles per liter decreases and the reaction moves in a direction where moles per liter are increasing. So that means introducing gas at constant pressure will subject a reaction to a kind of stress. Now let's do question and answers. First question is that we need to write the expression for Kc for the given reaction. Let's say we have a reaction 2SO2 plus O2, reversible reaction, and we get 2SO3. So if we have to write the expression for Kc, we know that Kc is equal to the concentration of products divided by the concentration of reactant raised to their respective moles. So let's apply it to this equation. So we'll have Kc is equal to concentration of SO3 raised to the moles, that is 2, divided by concentration of reactants raised to their respective moles. So this is how we are going to write the Kc expression for any reaction. Next question is, what will be the effect on K if the pressure is increased? We know that K gets affected if we change the pressure. And what is the effect? If we are increasing the pressure, then what happens? Moles per liter increases per unit volume. So what happens when moles increases per unit volume? it will shift to the direction where moles per liter decreases, right? So in this case, pressure is increased. So pressure is increased. So let's count the moles first. On left hand side, the moles are 2, and on the right hand side, the moles are 4. So if pressure is increased, then the moles are increasing, moles per liter are increasing. So it will shift the direction, or you can say the reaction, to a direction in moles per liter decreases. So in this case, moles per liter are less on the left hand side. So that means this reaction will be favored. So it will be an effect of pressure on K. Define catalyst and how it affects the equilibrium. So what is catalyst? Catalyst is a substance which affects the rate of reaction, without getting affected. Without getting affected means that the state, the quantity of the catalyst, etc. won't change. It is going to remain as such. It will just increase the rate of reaction. The second thing is that, does it affect equilibrium? No, it doesn't affect the equilibrium, but it can actually help the equilibrium point to achieve early. It can help the equilibrium point to achieve faster or early, whatever you can say. Next question is, define Le-Chatelier's principle. We know that Le-Chatelier principle is a principle according to which we can actually explain the factors that are affecting the equilibrium. So according to it, that if an equilibrium is subjected to any kind of stress, whether it is a stress of the increase or decrease in concentration, increase or decrease in pressure, or you can say the presence of inert gas, anything. So if an equilibrium is subjected to any kind of stress, then the reaction proceeds in a direction in which the stress gets reduced. So this is what is Le-Chatelier's principle. Let's take an example also. Let's say if we have a reaction like this, that is the formation of ammonia. So we know that K is written as the concentration of product raised to the respective moles, the concentration of reactants raised to their respective moles. Now, if in case we increase the concentration of nitrogen, so that means the reaction will get disturbed because it will be subjected to a kind of stress because the concentration of N is increased from the normal amount. So, but in order to keep the K constant, what happened? The reaction will be favored in forward direction. That is in a direction which the N2 gets consumed. So in forward direction it is getting consumed and it is getting converted into ammonia. So in this case the forward reaction will be favored in order to keep this K value constant. Thank you for watching this video, and for more learning experience you can visit www.wasscerats.com. So I think you are familiar with this chapter now.